for tomorrow. So let's start with how these Andreev-bound states originate. So in fact, the problem is here one has some non-superconducting region and the two superconducting electrodes. And the problem can be just studied as a scattering problem. So let's consider this very simple case where this coherent conductor is described just by a single conduction channel. So here there are electrons in a one-dimensional case, and they have just a free electron dispersion relation. So one can take an electron which is occupying this state and is traveling to the right in this case, and it arrives to an interface, the interface between this normal part and the superconductor. If this electron has an energy which is smaller than the superconducting gap, it's clear for all of you that if you just take a look at the density of state, there are no available propagating states on the superconductor side. So what happens? So in principle, there is a possibility, which was shown by Andreev, there is a possibility for this electron to take a companion from the superconductor, form a Cooper pair, and then just this can be seen as an evanescent solution inside the superconductor. On this side, this can be seen as a reflection of a hole. So this is the process called Andreev reflection. An electron comes here, is reflecting as a hole, and you can see that the charge that enters in this side is 2 times E. So it's the charge of a Cooper pair which is transferred to this side of the superconductor. Due to this process of Andreev reflection, the electron and the reflected hole acquires a phase, and this phase depends on the phase of the superconducting electrode and also on the energy of this incident electron with respect to the gap. So let me say that this effect of acquiring a phase after reflection is the same as when the light is reflected from a phase conjugating mirror. So it's the same effect. You can imagine now that this hole is going to travel back and find the other superconducting electrode, the other interface, and it can in turn be reflected as an electron, so following another Andreev reflection. So this is why the seen as a scattering problem is relatively simple. So we have quasi-particles which are occupying these conduction channels, and this quasi-particle can form, due to this Andreev reflection process, can form resonant situations. So this closed path, if one takes into account the accumulated phase, so in this Andreev reflection and in the other one, it's possible to find a resonant condition for the existence of these bound states inside this weak link. Of course, you can say that there are two things to take into account. One thing is that this weak link can be very long. For example, you can imagine a nanotube or a nanowire, something which has not zero length as an atomic contact, for example. In this case, one has to take into account the propagation. There is also a phase accumulated due to the propagation of the electron and the propagation of the hole. And this is taken into account, this as the k of the electron times the length of the system and the k of the hole. All of these phases can be taken into account in one single transcendental equation. So what is this equation? So let me go very slowly. So we have the k of the electron, the k of the hole, and the k of the electron and the k of the hole, they are both very close to the Fermi level, to the wave vector at the Fermi energy, so very close to here. And they can be just linearized, taking into account the velocity of this electron and this hole at the Fermi level. So using these two simple relationships, all this phase accumulation by the electron and by the hole can be just written in terms of a parameter which is lambda, which depends on the length of the weak link and the velocity. Just to say, in the equations it looks like, okay, there are a lot of parameters. Let's just say that we have to take into account the time of flight, the time the electron and the hole are traveling inside the weak link. So it's essentially the length over the velocity, and there are some constant to make it a dimension. So at the end, if we take into account all the phase accumulation, we get this transcendental equation, and this transcendental equation gives the relationship between the energy of this electron with respect to delta and the phase. The other thing that we have to take into account is the fact that there are also electrons traveling to the left. Why not? And these electrons traveling to the left they can give rise to another condition for this formation of this resonance state. The solution of this transcendental equation is just written here. This is the energy in units of delta, this epsilon here, as a function of the delta in the case when the length of the system is very short. So it's just in the limit of length equals 0. So this would be the case, for example, for an atomic constriction. I will come back to this in a second. So we have these energies. So we have these states which have an energy which goes from delta to minus delta, and they are just lying inside. If the system is not zero length, there are many of these solutions which appear inside the superconducting gap. So these are the cases. So this was the case for L very small, so L equals 0. If the length the system is made longer, so for example 0.8 or 2.5 in this adimensional parameter, what is important is that there are many of these Andre states that enter inside the superconducting gap. You can imagine that the system is very, very long. There are many of these states, and at the end one not see anything. So in an imperfect system, just to complete this picture of Andreev states, in an imperfect system there may be some scattering. If there is some scattering, then what happens is that electrons and holes that traveling to the right are coupled to the quasi-particles traveling to the left. It's just normal scattering. So for example, an electron which is traveling to the right can be also scattered at this scatter, this is like some barrier, some impurity, something which is just giving some normal scatter in the system. And in this case, the Andreev states that they are just at this point where these two solutions cross. This thick line corresponds to an electron traveling to the right, and this dashed line corresponds to an electron traveling to the left. At this point, they mix, and they give rise to this Andreev bound state, which have which have some gap here, and this gap depends on the transmission which characterizes the scattering. So this is just the case of a very short system. In the other cases, it's just what happens is very similar. So instead of having these these ballistic lines, we have Andreev bound state with some finite transmission. In this case, the transmission is 0.9. So I changed this. This is the results for different transmissions. For example, so we have in the short limit. So we have ballistic case. We have as we go to smaller and smaller transmission, you can see the states get just very close to the superconducting gap. So very close to here. For example, for a transmission 0.2, the states are almost very glued to the gap. In this case, so this can be seen in this expression, what is important is that if we have an energy which depends on the phase, as Dieter showed this morning, we can have a supercurrent, which is the derivative of the energy with respect to the phase. So we have this Andreev bound state, we have some energy, and we have also this supercurrent, which is the derivative of the energy with respect to the phase in the appropriate units. And this also depends on the transmission and on the phase difference. So you can see for the case of, let's take the green case, so the ballistic case. In the case the transmission is very large, the current, the supercurrent, is very non-sinusoidal. On the contrary, as we go to smaller and smaller transmissions, we get something which is very much like a sinus. So which is the connection between this Andreev bound state and the Josephson effect? So at the microscopic level, the Andreev bound states are the ones that carry the supercurrent. So for example, if we take a superconductor insulator superconductor junction, in this case there are many channels, many of these channels, and all of them have a transmission which is very small. In this case, just the spectrum of these Andreev states looks like this. So all the states have Andreev states which are very close to the superconducting gap. And in this case, it's very simple to, there are some numbers. So the number of channels is related to the surface of the area of the junction and the Fermi wavelength square, and the transmission are very, very, very small. So in this case, we can just take the energy of the Andreev bound states, the same expression I was showing before, and just sum over all the channels and take into account that this transmission is very small. If one makes the development, one finds just an energy, so we have some constant and an energy which is dependent on the cosine of the phase difference. So one recovers the Josephson relation for the energy, which we saw this morning. So this is like the microscopic demonstration of this Josephson coupling energy, which is related to, of course, to the number of channels and the normal resistance of the junction. What about the current? So just if we have this, if we sum over all the contribution for the channels, we recover the I naught sinus delta, where I naught, so the critical current is related by the Amagaoka-Baratov formula and related to the number of channels. So from a microscopic point of view, the Andreev bound states are the ones that give rise to the Josephson effect. So here there is this is the IB of a normal superconducting isolated superconducting junction, and this is the superconducting branch. So to prove, so now we want to go to a situation in which we can prove something more some effect of this bound state, with really give some test of the contribution of these channels to in a not trivial situation like the Josephson effect, where there is just many channels and very small transmissions. So this is what I was saying. So I will just say that due to in a very simple weak link, we have this Andreev bound state with energies which depend on the phase difference, and they are localized within this superconducting gap. So okay, so questions here. So I will stop for a second. I don't know if I'm speaking fast or not. I'm just yes.
If it's a junction, so there's an insulator in between.
Yes.
Where do those electrons come from? There is no discussion. There's a vector.
Yeah. So you have to take into account how do you describe an insulator. In this case, the very simple model is to consider something which is diffusive. You have many channels with very small transmissions. It's a model for this. Yes, of course, this image of this picture of electrons occupying a well-defined channel is more clear, is more adapted when there is when the length of the channel is small compared to the mid-free path. So let's do. Yes.
Could you go back to there you plot the density of states of the electrodes, and then in the middle you have the density of states of whatever you put in the middle.
Exactly.
So the quasi-particle peaks are carried by the Andreev's bound states.
Yeah, this is a very good point. So normally it's not usual to see here, due to the formation of this Andreev bound state, you can see that there are states that detach from this coherence peak, or this peak at delta, and the quasi-particle density of states is also modified. So the continuum is not the same when you have Andreev bound states.
But this is very localized.
Yes, this is very localized. So these states live really just in the region of this weak link. They are bound states, and the effect is equivalent to a Fabry-Perot. It's just a Fabry-Perot, but instead of mirrors, we have two superconductors with different phases. Okay, so in order to prove some properties of these states, I decided that it was better to rely on experiments and to comment in detail the experiments. So, for example, one thing that one could prove is to get some, to measure the supercurrent in a situation in which it's not sinusoidal. So just to measure some non-sinusoidal supercurrent or current phase relation. In order to do this, or for example, there are other possibilities. For example, perform the spectroscopy, so measure all the levels inside the weak link, or drive transitions between these states. So in any of these cases, one would need some system which is very well controlled. When we have few channels, measurable transmissions, and in particular go to higher transmission, because this is the case when all these effects manifest. Also, it's important to get a phase biasing, to know at which phase we can do all of these things, and if we want to measure transitions, to be able to detect them. So these are some requisites for the experiments. So let's go first to how we get a well-controlled system with few channels and measurable transmissions. So for this in the group we performed during many years experiments in a very simple system, which are atomic contacts. So in this case, it's just a constriction in a superconductor, made in a superconductor. So one has a superconducting electrode, some region which is of atomic size, and another superconducting electrode, and one studies the transport properties of this system. How do we do this? So I will explain this. This is also valid for tomorrow. If you remember what I say today, I will just skip it tomorrow. But essentially what we do is we nanofabricate an aluminum suspended bridge. So here there is an aluminum cable, wire, and in this wire we just nanofabricate this constriction, and all this is made on a plastic substrate. So this is capped on substrate, and the idea is that we can place this substrate in here, where there is this mechanic setup which allows us to apply some force and to bend the substrate. This is made in a sense that all the stress is going to concentrate in this constriction, and this atomic contact can just break, and then we can come back until we get some very small contact on the size of one atom. So we can really go to the limit of we have just one atom contact between these two electrodes. So in the limit of one single atom, there are just few channels, and the number of channels are just given by the balance of the aluminum, which are just 3. So we have at the end just 3 channels. The system is very stable. We can just fabricate this and measure during months, and we have some control. We have mechanical control of the transmissions. All the experiment is performed at dilution temperature, so at 20 millik's, where the aluminum is well below the TC, the transition temperature. So, yes?
How do you know that you have only one atom?
I will show you in a second, but it's a very good question. Yes?
Does the number of channels have something to do with the band structure of aluminum?
In this,
We have been hearing about band structures.
yeah, so it's a good question. So if one would like to make a model, a detailed microscopic model of what happens here, I can just, for example, here, what we observed is that it's, if you, for example, measure the transmissions, I will show how you measure the transmissions. As a function, as you just bend the substrate and come back, you don't get exactly the same. But because all these transmissions depend on all the environment seen by the atomic contact, and in this case I think it's more chemical advanced, because it's really a bit messy when you fabricate this break and come back. It's not very crystalline. So how do we know? So for example, this is the conductance as a function of the compression as we bend, and then you can see so this is the setup is like this, and we have a voltage, we have a current flowing. The conductance is just the slope. Okay, so what we get here is something, as we just bend, we go some conductance at some value, then there is a jump. We have these plateaus. These are like our conductance plateaus. This is, let me say that this is not, we don't expect something like goes like 2 square over 4 square over h, 2 square, something like this. We have these values in units of 2 square over h are 2, 4, 6, 8 here, but we just see steps. What is important is that just changes by steps because we have some arbitrary transmission, and at the end we get this very small conductance. And this is all the experiments is made with some magnetic field in only to be in a normal state. So this is the normal conductance. Okay. At the end here there is a zoom to this region where we can see the tunneling. So once we have separated completely the two electrodes, there is just a tunnel contribution, which is exponentially small. So what happens when we take out the magnetic field? So the system becomes superconductor, and then we measure the IB. Okay. So this is an IB curve. So this is the current, and this is here we have 60 nanoamperes, and this is the voltage, and this is 300 microvolts. So you see that we have some supercurrent. So there is, even in this one atom system, there is a supercurrent flowing. There is some quasi-particle branch as a standard Josephson junction, and there is some stuff here which are caused by what I'm going to explain in a second, which are multiple Andreev reflections. So these are sub-gap structure. Okay. So let's compare with the tunnel junction. So this is a tunnel junction which is aluminum oxide, measured at 40 milli-K. You see there is this supercurrent. There is this jump at 2 times delta, which is the jump to the quasi-particle branch. And if I put both together, so I get supercurrent, I get something which is at 2 delta, and there are also these features that appear in the middle. So what are these features? So this is like not new, and this theory was developed to explain and to see what happened in the presence of, which is the contribution to the IB for these Andreev states. And the idea is the following. So let's take the two superconductors here. At this point, when the voltage, so now we have an experiment with applied voltage. Now it's a non-equilibrium situation. So when the voltage is in units of E is 2 times delta. So at this point, an electron has enough energy to jump from one superconductor, from one electrode to the other one. So this is standard standard jump to the quasi-particle branch. If one goes to the minus voltage, one gets the same, but for the holes. Okay, just quasi-particles are holes in the other voltage. So what happens at this particular case when the voltage is 2 times delta divided by 2? So in this case, so due to Andreev reflection, there is a possibility to take an electron, make a Cooper pair here, and be reflected as a hole. And in this case, you give half of the energy to the electron and half of the energy to the hole, which is completely possible because the hole is traveling in the other sense. So this contribution, this extra contribution exactly at this voltage gives rise to this increase in the current of the complete constriction, complete with link. Of course, there are many of these processes. One can continue to here 2 times delta over 3, and in this case, an electron suffers Andreev reflection, transfer a Cooper pair, it's reflected as a hole. The hole takes another electron from here, which or takes another, if you want, another hole, making also a Cooper pair traveling in the other direction. Okay, so the energy can be divided in this way, in these quasi-particle processes. And of course, in this case, charge, which is the charge that is transferred. So in this case, the charge is E. In this case, the charge is 2E. And in this case, the charge is 2E plus E. So there are, as we continue, the charge can be just transferred in this way. Each of these process, so since in this case these quasi-particles occupy the unwave states, and these unwave states are characterized by some transmission. So this process happens with a, you see there is a, well, I don't know if you see, I see more or less. So there is a barrier here. So this electron goes to the other side with probability, with a process which has probability tau. This process, we cross the barrier twice, so quasi-particle cross twice the barrier, so this is a process which goes like tau square. And this process goes like tau to the cube, etc. So you can see that the rest of the process we don't see anything. But what is important is from, well, this is not, so these non-linear features in the IB depends very much in the transmission. So if the transmission is one would get something, just a lot of contributions giving rise to something which goes directly like this. And if the transmission is very small, then we don't get anything. Okay. So an atomic contact is in the middle. So let's see how we get this. In particular, we have to add the contribution, as I said, in the limit of one atom, we have 3 channels. So these channels, for example, if we take one with 0.47 transmission, 0.24, 0.05, in this case, if we add all these contributions, we get this. How we know that these are this is the good fitting and not another one? Because this is a really a very nonlinear signature in the IB, and in this case is very hard to get good fitting with whatever parameters. It's really, you can just get the good ones, and from this measurement you can really extract the transmissions. Okay. Well, I will just a comment. The system is very nice. We can just open and close, and form different systems with different transmissions. And we have shown a case where the transmission was almost 0 to a case where it was almost 0.999. Okay, very ballistic. So in all these cases, we get some intermediate, which you can remember from this picture. So this shows that we have, what is important here is we have some contribution from unwave states. We have a system which is well controllable and with measurable transmissions. Okay. So, well, I can comment if indeed the last one if you want. This is just a measurement of the transfer charge, but it's so in more recent experiments we made the same thing but in semiconducting nanowires. So the idea is the following. So this is a semiconducting nanowire made in indium arsenide, and this nanowire is covered with aluminum. It's fabricated in Copenhagen, and the system is like this. So you have this indium arsenide here in the center. All around there is aluminum, and this is grown with in MBE with epitaxial precision. So the aluminum here is just at the interface between the indium arsenide and the aluminum is of atomic perfection. What the effect of this is that the proximity effect from the aluminum to the indium arsenide. What I mean from proximity effect is the ability of the superconducting correlations in the aluminum to leak, to go into the indium arsenide, are very, very good. So the electrons in the aluminum they behave as in the electrons in the indium arsenide, they behave as in the aluminum. So, well, to prove this, for example, people just fabricated a junction. They proved they measured with a tunnel probe, and I will leave Dimitri to explain a tunnel probe on STM in a second. I will just say that they measure the superconducting gap of the electrons of the wire, and what they measure is this blue line, epitaxial here. Epitaxial, this is the density of states of the electrons of the wire, and they can see that this really like the electrons of the aluminum with a very hard gap. Okay. This is this is in log scale to show that there are no contributions to the gap. This is just a characterization of the system. What I want to say is that we perform the same experiment. So measure the current, the IV characteristic of this system, as a function of the gate voltage. So let me explain in 1 second. So the weak link here, how we make the weak link. So what we do is to just take out some aluminum in some region of the wire. So here, in some length of the wire, we just etch the aluminum. So what we get is superconductor, wire, so naked wire, superconductor. And in this case, in this normal region, we can apply a gate voltage to tune to gate the wire. Yes. The question? All right. So in the same case as before with the atomic contacts, we're playing with this mechanical control. Here we can just we can control the number of channels with the